So welcome back. We are now working on section 9.4, which is transformations of the plane. Up until now, we've of course learned what a matrix was. This is the idea of the chapter. What is a matrix? And we've also come up with some examples of using matrices. And in this section and the next few sections and chapter 15, we will be doing lots of more situations of how matrices can be used in various situations. In this section, it's about transformations. And we're going to start by looking at example 6 on page 391. And we're going to talk about 4 types of transformations that are called linear transformations. There are other transformations that are linear besides these 4, but these 4 are the ones that we're focusing on at the beginning of section 9.4. And what we have to start is we have a plane, a coordinate system. We only need, for this particular example, the first quadrant, or at least we're starting with only needing the first quadrant. And we have a shape in this quadrant, and it is a triangle. That's horrible. Let's try that again. So 1, 2, 3. All right, we got a triangle. And we are going to do 4 things with this triangle. And these are some of the transformations that we'll be working with. Part A says, draw the image of the triangle after a rotation by 90 degrees counterclockwise about the origin, or the point 0, 0. So the first of our transformations is a rotation. We want to rotate this object. Now, I don't mean take the triangle and rotate the triangle where it is. That is its own transformation that we're not worrying about. We are rotating it about the origin, which means if you imagine taking drawing a line from the origin to any point on the triangle, for example, to that point, we want to rotate this line by 90 degrees counterclockwise, something like that. And the image of that point would be over there, assuming I did it correctly. We want the same length, so it's kind of hard to do these by hand, which is why we have matrices do them for us. But one way that you can do it, especially on the iPad, is you can imagine drawing a circle centered at the origin through various points. And when we rotate by 90 degrees clockwise, we are basically rotating these points along the edge of the circle. So if we start at, let's say, a 45-degree angle, because it's 1 to the right and 1 up, and we go 90 degrees, we should end over here, which is a 90-degree rotation. And if we start here at this point right there and go 90 degrees, we should end over there. And of course, then we would connect those 2 points. And if I would do the same thing with this one, I should get a triangle that looks something like this. If I then remove all these extra things that don't want to remove that one. So to a first approximation, the image of that original triangle would be right over here. That would be a rotation by 90 degrees. That's just the first one. That's a rotation by 90 degrees. And what we're going to see is that we don't need to do any of this stuff. We don't need to draw circles. We don't need to really imagine it. We are going to have matrices do everything for us. It's going to be wonderful. The second one is a reflection. A reflection in the line, in this case, in the line, x equals 0. What is x equals 0? X equals 0 is the y-axis. So we are reflecting this over the y-axis. And if I would reflect it, it would look something like, no, that's not a reflection. It would look something like this goes here. It would look something like that. So that would be a reflection over the line x equals 0. And again, matrices will do it for us. So we have a rotation, counterclockwise or clockwise by a given angle. We have reflection over a given line. Next, we have an enlargement, scale factor 2, center 0, 0. An enlargement. And the notation, enlargement scale factor 2, center 0, 0. Very succinct, very precise. But what exactly does it mean? We want to take the figure and we want to make it twice as big. It's an enlargement scale factor 2. What does that mean, make it twice as big? Well, you can make it twice as big, but where do you put it? So the answer is, you look at the coordinates. For example, this point here is 1, 1. And when you make it twice as big, then x becomes 2, y becomes 2. And now we're over there. This point here, which was 3, 1, is going to end up at 6, 2, way out, not over there, 6, 2, about here. And this point here, which is 3, 2, is going to end up at 6, 4. And we see that we have the triangle like that. It's twice as big, but the x coordinates and the y coordinates themselves were moved over like that. And then the fourth one is D, is a stretch. A stretch parallel to the x-axis, scale factor 2. What is a stretch parallel to the x-axis? That means here's the x-axis. We're stretching it this way. It's not an enlargement where both x and y stretch, but rather it's a stretch parallel to the x-axis. So the x values double, but the y values stay the same. So if I started 1, 1, and I double my x value, but keep the y value the same, I'd be here at 2, 1. 3, 1 goes to 6, 1. 3, 2 goes to 6, 2. And I would have a triangle that looks something like that. So these are the 4 basic transformations that we're going to be dealing with in section 9.4, or at least the first part of section 9.4. Now, if you take out your formula book, you will see that it has the following, which is really nice to have. And we're going to be using these matrices throughout this section. We're not going to be doing things without them. So going through them, the first one is a reflection in the line. That's not how you spell line. In the line, y equals tangent theta x. Now remember, a line is y equals mx plus b, where b is the y-intercept. In this case, the y-intercept is 0, which means these lines have to go through the origin. And tangent theta is my slope. So the slope is connected to the angle. How is this the case? Well, very easily demonstrated. If you have a line that goes through the origin like so, and you give me any point on the line, I can draw a right triangle here. This is the rise, this is the run. So what is the slope? Slope is rise over run. But if I look at this angle here, theta, then tangent of theta is opposite over adjacent, and that's also equal to rise over run. So we see that the angle of inclination, or angle of elevation, is intimately connected to the slope itself. And sometimes you might have the slope and need to find the angle, and sometimes you have the angle and you need to find the slope. Either way, as our first matrix, the matrix of transformation is cosine 2 theta, sine 2 theta, sine 2 theta, negative cosine 2 theta. This, as we'll see how this matrix is used. But this 2 by 2 matrix is reflection in the line y equals tangent theta x. Our second of our matrices is a horizontal stretch, or in other words, stretch parallel to the x-axis. It might use either notation for that, with scale factor k. And that is K001. Again, I'm not proving any of these. I'm just giving them to you. A vertical stretch, or a stretch parallel to the y-axis with scale factor k, will be not 0, sorry, will be 1, 0, 0, k. Next, if we have an enlargement with scale factor k, center 0, 0, maybe you can kind of discern what it is, because an enlargement is both stretching in the x and y directions. And as we see, a stretch in the x direction has a k in the first row, first column. A stretch in the y direction is a k in the second row, second column. You want to do both, so we will put a k in both of them. Next, we will have a counterclockwise rotation of angle theta about the origin. And this one looks very similar to the reflection, with a couple differences. First, we don't double the angle. We just do cosine of the angle, sine of the angle, and so on. And while the first one had the negative sign on the bottom right, this one has the negative sign on the top right. So 2 changes for a counterclockwise rotation and a reflection. And finally, if we have a clockwise rotation of angle theta about the origin, that will be very similar to counterclockwise. And in fact, this one is about halfway between, not halfway, but this one is another situation where we put the negative sign this time in the bottom left, but other than that, very similar to counterclockwise rotation as well as to the rotation. So with that all under our belt, and we now have all of our matrices that we need, let's go ahead and actually do a problem and see how we use these matrices to perform transformations. So we're going to do example number 7. Part A. It first says, write down the matrix that represents a rotation of 45 degrees anti-clockwise about the origin. Well, when I go to my sheet, my formula sheet, or the, I can always look back at the video as well. We have a counterclockwise rotation. That's this matrix right here. The only thing we got to do is put in 45 degrees. So it's going to be cosine 45 degrees, negative sine 45 degrees, sine 45 degrees, and cosine 45 degrees. What are those values? Well, the book is so nice, and it tells us that cosine 45 degrees and sine 45 degrees are both 1 over the square root of 2. So 1 over the square root of 2, negative 1 over the square root of 2, 1 over the square root of 2, and 1 over the square root of 2 would be our matrix that represents a 45-degree rotation counterclockwise about the origin. Part B. Write down the matrix that represents a horizontal stretch of scale factor square root of 2. Horizontal stretch of scale factor square root of 2. That's just square root of 2, 0, 0, 1. Again, go right to your formula sheet or what I wrote down a few minutes ago. C. Now, hence means using the information that you just established, find the image of 2, 3. So here is 1, 2, 1, 2, 3. So here's the point 2, 3. Find the image of 2, 3 after a rotation of 45 degrees anti-clockwise about the origin, followed by a horizontal stretch of scale factor the square root of 2. Where does this point end up? If I don't use matrices, then I have to kind of imagine a circle here. That's a horrible circle. Let's try that again. Imagine a circle. I want it to go through. Okay, there's my circle. It's a 45 degrees. 45 degrees would be along the y-axis. So it would end up over there. No, that's not even 45 degrees because I wasn't at 45 degrees. So it's somewhere like over here somewhere. And then stretch it, a horizontal stretch by a scale factor square root of 2. That means I would go like over here somewhere or something like that. You see how hard it is to do it by hands? It's extremely complicated. And you got to be really good at art. And that's not something that I am. So here's what I'm going to do. I'm going to take my 45-degree rotation matrix, which is 1 over root 2, negative 1 over root 2, 1 over root 2, and 1 over root 2. And I'm applying it to the point 2, 3. So what I can do is I can use 2, 3 as my matrix. Sometimes the book will call it a vector, which we'll get to in other sections. Vector, matrix, same thing. A column vector and a matrix, sorry, a column matrix and a vector, the same thing. So I can apply it to 2, 3. I know how to do this. This is just basic matrix multiplication. And then don't forget, after I get that answer, it says apply a horizontal stretch of scale factor the square root of 2, which is just that. And this is just straight up matrix multiplication. So I'm going to first do the last two. So 1 over root 2 times 2 minus 1 over root times 2, 1 over root 2 times 3 is negative 1 over root 2. And then 2 over root 2 plus 3 over root 2 is 5 over root 2. And then I can do these as well. And I get negative 1, comma, 5 over the square root of 2. Which, if you remember my picture that I tried to draw, which wasn't the greatest, that's somewhere in the vicinity of the correct answer. but -1, 5/√2, that is the correct answer. Much faster and easier than doing it by hand. Now it says write down the single matrix that represents a 45-degree rotation followed by a horizontal stretch of scale factor, the square root of 2. What we did, if you look in part C, is we applied the first matrix, which was the first transformation, got the answer, and then applied the second transformation. But what we could do is we could actually first combine the transformations into a single transformation and then apply that to 2, 3. And if I would do, because remember, matrix multiplication is associative. If I have 3 matrices, 1, 2, and 3, that are being multiplied by each other, I can do the second and third, get the answer, and then do the first by that, or do the first 2 together, get the answer, and then do the third. So if I do this, let's see what I get. Top left, I get 1 over y, okay. Bottom left, I get 1/√2. I get -1, and then 1/√2. So this matrix here is the matrix that is represented by both transformations, one after each other. And in fact, that's such an important concept that we can bullet it and put it in a bubble. It says, if a transformation represented by a matrix A is followed by a transformation represented by matrix B, then the single matrix that represents both is BA. Now it's important to notice one thing. If you do A first and then you do B, A is to the right of B when they're put together. Because if you look back here at part C, here is matrix A, here is matrix B acting on my vector V. If I first do A and then do B, A is applied to V, answer, B is applied to that. So the one that you do first should be on the right, not on the left, which is, I guess, probably a more familiar location when they're done in succession. And this is a really good property to have, because if I perform like a rotation by 45 degrees and then a rotation backwards by 45 degrees, I'm back to where I started. Wouldn't I rather combine those two matrices into the identity matrix? Because what is the identity? It gives you back what you began with. Rather than first rotating and then rotating back, I can conceptually combine them together into one and then do that, and it's a lot less work. But of course, same answer either way. So here is example 8. Now this is a different type of transformation. It's not any of the ones on our list. It's not an enlargement, it's not a stretch, it's not a rotation, it's not a reflection, but it is a linear transformation, which means it can be represented by a matrix. And that's key. Linear transformations are represented by matrices. In this section, until the exercises at least, because there is a part at the end that deals with nonlinear transformations, everything is linear. Okay, so the question says, find the 2 by 2 matrix that will take the point 2, 1 and move it to location 1, 4, and take the point 1, -3 and move it to location 4, 9. So we have 2 points that are being moved, and we want the matrix that will do this for us. Because then if I give you any other point, like for example, if I say, hey, where does 17, -12 go? You can say, well, no problem. Let me find the matrix of transformation and then apply it to 17, negative 12, and then wherever I end up is where I end up. So how do I do that? Well, the first thing to notice is we are looking for a 2x2 matrix, and we currently do not know any of the 4 entries. So we'll call them A, B, C, D. These are the 4 things that we are looking for. What is A, B, C, D? I don't know, but I do know the following. If I apply that matrix to the point 2, 1, it should give me the point 1, 4. And if I apply that same matrix to the point 1, negative 3, it should give me the point 4, 9. So I have 2 matrix equations, but I have 4 unknowns. So I need 2 equations more, right? 4 unknowns, you need 4 equations. But I actually have 4 equations, as you're going to see in a second. Let's write out the matrix multiplication for each of the 2 matrices that I have. The first one, ABCD times 2, 1. That gives me, if I look at the top row, it gives me 2A plus B equals 1. And the bottom row, 2C plus D is equal to 4. Second matrix, I get A minus 3B equals 4. And C minus 3D is equal to 9. I have 2 equations that connect A and B. I have 2 equations that connect C and D. I can solve them each individually for A, B, C, and D, and therefore I have my matrix. So let's go ahead and do that. How do I solve the first 2 equations? Well, notice that the coefficient of A in the first one is 2, but in the second one is 1. So I'm going to keep the first row the way I have it and multiply the second row by 2. So I get 2A minus 6B is equal to 8. Now that I have 2A and 2A, I can subtract. 2A minus 2A goes away. B minus negative 6B is 7B. 1 minus 8 is negative 7. So B is equal to negative 1. Once I know B is negative 1, I can go ahead and plug it back in. Let's see in the second one. So I get A plus 3 equals 4, and therefore A is equal to 1 solved. I'll do something very similar in this case. Keep the first row, multiply the second row by 2. 2C minus 2C goes away. D minus negative 6D becomes 7D. 4 minus 18 becomes negative 14. D becomes negative 2. Once I know D is negative 2, I get C is equal to 3. And therefore, my transformation matrix is A, B, C, D. 1, negative 1, 3, negative 2. And now, if there was a follow-up, where does this point go? Where does that point go? I have my answer, and I can just do the math. Now, there is one more aspect of these transformations that is really, really cool. I know you're thinking, all math is cool, but this is in particular. When we had that original triangle, if I really wanted to, I could go ahead and I can compute its area. 1/2 base times height, right? If you look at the original triangle, base is 2, height is 1, 1/2 2 times 1. Hey, it has an area of 1. When I rotate it, area is still 1. When I reflect it, area is still 1. But when I enlarge it, the area changes. And the question you might ask yourself is there a way to predict the area of the image of a shape if you know A, the original area, and B, the matrix of transformation? And the answer is that yes. And that's, again, without proof, it just is this. Area of image is equal to area of original, or what the book calls the pre-image, times the absolute value of the determinant of the transformation. Of course, we need the absolute value because determinants can be positive or negative, or technically 0. A 0 determinant would mean that my original shape somehow, which is 2-dimensional, somehow collapses into a single dimension. You can have transformations that do that, although a reflection won't, a rotation won't, a stretch won't, and an enlargement won't. So none of our 4 basic ones will, but there are some transformations that do. But in general, you take the determinant, take the absolute value of the determinant, and multiply that by the original area, and you get the new area. And that one is our second key of this section, so our second bubble. So let's start now with exercise 9E. Question number 1. It says, find the transformation matrix for a bunch of cases. Oh my God, that's not straight at all. Find the transformation matrix for a bunch of cases. Now, I have my formula sheet right here that I'm going to keep right in front of me because all of these I'm going to find it on the rotation sheet. So first, a reflection in the x-axis. A reflection in the x-axis. Well, if you reflect in the x-axis, the angle of inclination is 0 degrees and tangent of 0 degrees is 0. Right? Of course, you don't need tangent of 0 degrees, you just need the angle. The angle is 0 degrees, which means twice the angle is 0 degrees, because if you look at your reflection matrix, we need twice the angle. So cosine of 0 degrees is 1, sine of 0 degrees is 0, the sine of 0 degrees is 0, and negative cosine of 0 degrees is -1. We get 1, 0, 0, -1, and we're done. B, an anti-clockwise rotation about the origin of 45 degrees. We did this already in the section, but it's cosine 45 degrees, which is 1/√2, negative sine 45 degrees, sine 45 degrees, cosine 45 degrees. Done. C, a clockwise rotation of pi/2. That's the last one on the formula sheet. Clockwise of pi/2. Cosine of pi/2 is 0. Sine of pi/2 is 1. Negative sine of pi/2 is -1. Cosine of pi/2 is 0. D, and hopefully you're stopping and pausing and doing all these on your own. Don't just copy them. D, a reflection in the line y equals -x. Well, here's y equals -x. It looks like this, which gives me a theta of -45 degrees and tangent of -45 degrees. I don't even need that. But notice that tangent -45 degrees is 1. But nevertheless, now that we know that theta is -45 degrees, theta equals -45 degrees, I know that 2 theta equals -90 degrees. So what does my reflection matrix say? Cosine 90 degrees, sine 90 degrees, sine 90 degrees, negative cosine 90 degrees. We get 0, 1, 1, 0. Part E, vertical stretch by a factor of 3. Vertical stretch by a factor of 3, 1, 0, 0, 3. Reading it right off the sheet. F, an enlargement scale factor 2, 2, 0, 0, 2. Done. If you know your matrices, and the horizontal stretch, the vertical stretch, and the enlargement are pretty straightforward, you just rattle them off. And finally, G, a reflection in the line y equals the square root of 3x. Y equals the square root of 3x, so something like this. We need the angle. Well, don't forget, tangent theta is equal to the slope. In this case, tangent theta is equal to the square root of 3. So what angle is that? Well, you should know your trigonometry, and if not, your calculator does, but tangent theta equals square root of 3. That means theta is equal to pi/3, which means 2 theta is 2 pi/3. And now I want a reflection. So I go to my reflection matrix. Cosine of 2 theta, cosine of 2 pi/3 is -1/2. Sine of 2 pi/3 is positive √3/2. Sine of 2 theta again is positive √3/2, and negative cosine 2 theta is -1/2. And we're done with question number 1. Moving on to question number 2. Write down the, this is part A, write down the transformation matrix for an enlargement scale factor 4, center 0, 0. No problem. Done. B. Write down the transformation matrix for a rotation of 180 degrees about 0, 0. Doesn't say clockwise or counterclockwise, just has a rotation of 180 degrees. Oh, but wait a second. If you rotate clockwise by 180 degrees and counterclockwise by 180 degrees, you're in the same place. So I don't care which one I use. So we'll use the first one. Cosine of 180 degrees is -1. Negative sine of 180 degrees, sine of 180 degrees, cosine of 180 degrees. We get -1,0,0,1, and we're done. Then it says, a rotation of 180 degrees about the origin, followed by an enlargement of scale factor k, where k is greater than 0, is often referred to as an enlargement with scale factor -k. So now, an enlargement with a scale factor of -k means rotate it by 180 degrees and then stretch it by a factor of k. So when you come across that, now we need to know that. C. Find the product of the two matrices found in parts A and B, and hence explain why this is justified. So if I first rotate by 180 degrees, -1, 0, 0, -1, and then enlarge by a scale factor k, notice how the one I did first, it's on the right, I get -4, 0, 0, -4, which is of the form of an enlargement with a -4 scale factor. So it seems very understandable, very reasonable why an enlargement of scale factor -k is interpreted as rotate by 180 degrees and then stretch by a positive scale factor k. Question number 3. Consider the triangle. Consider the triangle whose vertices are described by the following matrix. The matrix P is 2, 4, 6, 7, 10, 6. So what that means is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 2, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. And 10, 6. So we have a triangle. And that matrix, that P matrix, is 3 columns of 2 points each, and each of those is a location of the 3 points, the 3 vertices of that triangle. Hey, there's a picture there that does the same thing. So A, use matrix multiplication to determine the image of triangle A, B, C when it is reflected across the x-axis. So it's reflected across the x-axis to obtain triangle A prime, B prime, C prime. So we want to take 2, 4, 6, 7, 10, 6, and we want to reflect it across the x-axis. Well, if you look at my reflection x-axis, 0 degrees, my reflection matrix for 0 degrees, cosine 0 degrees, sine 0 degrees, sine 0 degrees, negative cosine 0 degrees. So I apply my rotation matrix, and I can do all 3 at the same time. Notice how I have 2 by 2 by 2 by 3 gives me a 2 by 3. So the first one goes to 2, -4, 6, -7, 10, -6, which makes a lot of sense. Because when you reflect across the x-axis, your x value is not changing, but your y value is becoming negative. So 2, -4, and there, and something like there. And that would be A prime, B prime, C prime. Sketch the triangle and its image on the same axis, and then triangle A prime, B prime, C prime is reflected across the y-axis to obtain A double prime B double prime C double prime. So what is the reflection across the y-axis? Well, if you reflect across the y-axis, then in that case, theta is 90 degrees. So I'm going to take my new matrix, 2, -4, 6, -7, 10, -6, and reflect it across the y-axis, where theta is 90 degrees. So cosine of 180 degrees is -1, sine, and then negative cosine 180 degrees is +1. So what do I get here? -2, -4, -6, -7, -10, -6, which again makes total sense because now it's the y values that aren't changing and the x values that are becoming negative. And you get something that looks like this. Now, again, not perfect, but A double prime, B double prime, C double prime. So you have your original reflection, then you have your final reflection. Now, part B says, write a single matrix equation to find the image of P is the original matrix, under the composition of both reflections. Well, I can combine the two matrices together. Just remember, the first one that I use, the first matrix goes on the right, the second one goes on the left. So what is the 2 by 2 matrix that represents both of these? Well, if I just do the math, I get -1, I get 0, right? -1, 0, 0, -1. So I get the same thing as a rotation of 180 degrees. A reflection is the same thing as a rotation of 180 degrees. Crazy. Or an enlargement scale factor, -1. C. Show that if the triangle ABC is reflected across the x-axis, then again across the x-axis, you get back what you started with. Well, it certainly makes sense, but let's do the math. If you reflected across the x-axis, which was 1, 0, 0, -1, and then again reflected across the x-axis, 1, 0, 0, -1, what do you get? You get 1, 0, 0, 1. You get the identity matrix because it's the same thing that you started with, which makes perfect sense. And then D, what transformation is equivalent to reflection on the x-axis followed by reflection on the y-axis? This is, as we just said, a rotation of 180 degrees. All right, so that takes us to the end of question 3. Moving on to question number 4. We having fun yet? I know I am. Question 4. A, write down the transformation matrix for a reflection of the line y equals tangent alpha x. Okay, I don't know why he's asking us to do that when it's on a formula sheet, but following directions is easy in this case because I have my formula sheet in front of me, so I can just write it. No problem there. That's A. B, verify that a reflection followed by a second reflection in the same line is equivalent to the identity matrix. Ooh, so if I do that matrix, and then I do this, I could have just copied it, but okay. And then I do the same matrix again, I should get the identity. And if I reflect across a line and then reflect back across the same line, I should be back to where I started with. Well, let's see if that's the case. Top left, cosine plus sine, cosine squared plus sine squared. Ooh, trig identity, that's 1. Next one, cosine sine minus cosine sine, cancel. Bottom left, cosine sine minus cosine sine, lovely, cancel. Bottom right, sine squared plus cosine squared. Ooh, identity 1. I do in fact get the identity. Isn't math grand? Question number 5. Write down the exact matrix R for a rotation of 45 degrees clockwise about the origin, not counterclockwise, which is R. Oh, actually, we have both. No problem. So clockwise 45 degrees, cosine 45 degrees, sine 45 degrees, negative sine 45 degrees, cosine 45 degrees. They're all 1 over root 2 because, well, they gave it to us earlier. Then it says find the value of r to the 8. So this is r, my rotation matrix. So we want the value of r to the 8. Well, I could take out my calculator and put this into my calculator, take it to the 8th power, get an answer. I can certainly do that, but it's so much easier. If you rotate by 45 degrees and you take that to the 8th power, you're essentially rotating by 45 degrees 8 times, because you're doing the same matrix 8 times. Rotate, 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 rotate 8 times. 45 degrees times 8, that's 360 degrees. Hey, I'm back to where I began. This is the identity matrix. So r to the 8 is just 1001. And interpret your results. This is the identity, right? Nothing changed. It's the identity transformation, leaving everything where it is. Question 6. Find the area of the triangle with vertices Find the area of the triangle with vertices 0, 5, 4, 5, and 2, 7. So we just want the area. Well, luckily, this one has a base that's horizontal and a height, of course it's vertical. This one's very easy. You can just do 1/2 base times height. 1/2, the base is 4, the height is 2, so the area is 4. Now, that was part A. Part B says, use the result that the area of the image is equal to the absolute value of the determinant of the transformation matrix times the area of the original object, which is that bubbled formula that I gave you at the end, to find the area of the image after the following 2 possibilities. 1, vertical stretch with a scale factor 2. So vertical stretch with a scale factor 2. So I don't, that's bad shorthand. I'll just write it out. A V stretch with scale factor 2, followed by an enlargement. So followed by enlargement about the origin scale factor 3. And we want the new area. No problem. All we got to do is find the determinant of the transformation matrix and take its absolute value. Well, we're first doing a V stretch with scale factor 2. That's 1002. Followed by an enlargement about the origin scale factor 3. So my total transformation is the product of these 2 matrices, which I can write as the individual matrix, which is 3, 0, 0, 6. And therefore, the determinant of the transformation matrix is equal to 3 times 6 minus 0 times 0 is equal to 18. Its absolute value, of course, is still 18. So the new area, and do they have a symbol for it? No, they don't. So we'll just say area prime. The new area is 18 times the old area. So the new area is 72. If instead I did just this transformation matrix, they don't tell me what this is. It's just some transformation matrix. Then what is the determinant of t? It's 10 minus -6 or 16. And therefore the area is 16 times 4, which is 64. Notice that a rotation matrix would have to have a determinant of 1 or -1, because the area does not change when you rotate. And a reflection matrix also would have to have a determinant of 1 or -1, because again, its area does not change when you rotate. Just, fun facts, impress people at parties and stuff. 7. Prove that, look at what I just said. Prove that neither transformation will change the area of the object by considering the determinant for a reflection and for a rotation. So A, Reflection first. We know that the transformation matrix that represents a reflection is cosine of 2 theta, sine of 2 theta, sine of 2 theta, negative cosine of 2 theta, and therefore the determinant of the transformation matrix is negative cosine squared of 2 theta minus sine squared of 2 theta, which is negative 1. So what's the absolute value of the determinant? It's 1. Area does not change. How about a reflection? Sorry, that was a reflection. How about a rotation? Well, there's 2 different rotations, depending if it's clockwise or counterclockwise. So we'll say T1 or TC for T clockwise is cosine theta, sine theta, negative sine theta, cosine theta. And what is its determinant? What's the determinant of TC? Cosine squared plus sine squared, straight up 1. I don't even need the absolute value. And counterclockwise is cosine theta, negative sine theta, sine theta, cosine theta, and the determinant of T counterclockwise, cosine squared minus negative sine squared, cosine squared plus sine squared, also 1. And we see what I just said, that a rotation and a reflection, and why can't this make a line? A rotation and a reflection do not change the area. Their determinants have to have 1 as 1 or negative 1, so that the absolute value is 1. Notice that the rotations are 1 and a reflection is negative 1. And there is a reasoning behind that. A rotation, this is a little advanced, but a rotation you can affect by not removing it from the flat surface, whereas a rotation, whereas as a reflection, you're changing the orientation. If you look back here at this one here, the original matrix ABC, you go clockwise from A to B to C, but in the reflected matrix, you go counterclockwise from A to B to C. And then you reflect twice, you're back to clockwise, A to B to C. You can only do that if you actually remove it from the plane and go into the 3rd dimension to affect the change, which is where the determinant of negative 1 comes from. More advanced than you need for the course, but it just shows you that, out there in math world, there's a lot of really some cool stuff. Question 8. You have a linear transformation T represented by 3, 5, 2, 4. This is not any of our shifts, reflection, rotation, stretching of any kind. It's just some random transformation matrix. A. Find the coordinates of the point 14, 12. Well, no problem. Take your matrix and apply it to the point 14, 12 and see where you end up. 3 times 14, that's 42, 42 and 60, so I get 92, and then 28, and 48 is 76, so I end up at 92, 76. B, what are the coordinates of the point having an image of negative 12, 12? So now I know where I end up. I know I end up at negative 12, 12. I know my transformation matrix, but what are my points A, B? How do I solve this? No problem. We know matrix stuff. Look at the matrix on the left. Its determinant is not 0. 12 minus 10, so it has an inverse. So multiply on the left by that inverse, and you get the inverse of 3, 5, 2, 4, negative 12, 12. All I got to do now is find the inverse. Well, it is a 2 by 2, so I know how to do that. You flip the main diagonal elements, you negate the off diagonal elements, and then you divide by the determinant, which is 2, negative 12, 12. I can incorporate the negative 2 as a constant in. I don't want to do it into the first matrix because then I'll have fractions, but I could do it in the second matrix, and that gives me smaller numbers. So negative 24 and negative 30, negative 54, and 12 and 18, 30, if I did it correctly. And I just solved for the starting point that goes to the point negative 12, 12. What about numero 9? New transformation matrix. This one is -1, 2, 1, -2. And now A, we want to find, this is like the same as number 8, a little redundant, but find the coordinates of the point -3, 4. So -1, 2, 1, -2, acting on the point -3, 4 gives us 11, -11. Oh, how cute was that? 3 plus 8 and -3 minus 8, yeah. And then B, find the coordinate to the point having an image of -12, 12. So -1, 2, 1, -2, acting on what gives me -12, 12. So same thing. AB is the inverse. What's the inverse? Flip those, negate those, divide by, This one does not have an inverse. This one does not, this is why it's not merely a repeat of the previous question. It seems that even though this matrix will transform -3, 4, there is no point that transforms to -12, 12. Either that or there are multiple points because it has no inverse. So there's no unique solution. So which case is it? Well, let's take a look. Let's actually do it the good old-fashioned way by solving for A and B. I have -A plus 2B equals -12. I have A minus 2B equals +12. And these two equations are really the same equation, because if you multiply the first or second by -1, it turns into the other one. So really all I need is A minus 2B equals 12, which has infinitely many solutions. So the answer is, it's all points A, B, such that A minus 2B is equal to 12. There's actually infinitely many points that map to -12, 12. All you need is any point such that A minus 2B is equal to 12. And if A minus 2B is equal to 12, for example, 12, 0, 12, 0 will map to the right place. So will lots of others. That was kind of cool. Unexpected, actually. I wasn't expecting that to happen, and they surprised me. Question number 10. Find the 2 by 2 matrix that takes the point 2, 1 to the point 1, 4, and the point 1, -3 to the point 4, 9. Well, we did an example like this. The currently unknown matrix ABCD, when acting on the point 2, 1, gives me the point 1, 4, and the currently unknown matrix ABCD acting on 1, -3 gives me 4, 9. So the first one gives me 2A plus B equals 1, and 2C plus D is equal to 4. Second one, A minus 3B is equal to 4, C minus 3D is equal to 9. How do I solve these? Well, the same way we did it before. Let's multiply. Let's keep the first rows the same. So the first row is the same. Let's multiply the second row by 2. This looks really familiar, but can we do this one? What was their example from before? 2, 1 to 1, 4, and 1, -3 to 4, 9. That is so strange. We did this one already. Okay, that's just weird. So I'm just going to do ... because I don't got to do it twice. Our transformation matrix is 1, -1, 3, -2. That's so strange. I'm going to pause for a second, and what I'm going to do is I'm going to look at their, they have a list of errors and mistakes that they've made in the books. I'm going to check whether or not anyone's noticed this, so I'll be right back. And sure enough, I do see here on the list, it does say page 397, 9E, number 9. Oh, the previous one also was a mistake. Maybe that's why. Oh, guys, you're killing me here. Okay, maybe that's why That's why I was a little surprised that they would ask something like that. So let's go back over the previous one, number 9. It says change -1 to -2. So we're going to make that -2 instead. This becomes -2, and this becomes -2. So then these are wrong. That should be 6 plus 8 is 14, and -3 minus 8 is still -11. But now this changes everything. In fact, I'm just going to delete all of this work because the next one also is wrong. Don't think of it as a waste of time, though. Oops, no, it's not wrong. Don't think of it as a waste of time, though, because seeing what happens when the determinant is 0, and therefore it has no inverse, was a little instructive. So where are we? Number 9. So okay, so let's do this now. So what is A, B? So those switch, which means you get the same thing. Those switch sign, and we divide by 2. 4 minus 2, -12, 12. So this gives us, I'm going to absorb the 2 into the other one. In fact, I'm going to absorb the negative signs also into the other one. Why not? Which gives me 6, -6. So I get 12 minus 12 is 0. And then I get 6 minus 12, I get 0, -6. So that takes care of number 9. Thank you, boys, for fixing that. Question 10. And it says that the first point should be 1, 2 changed to -1, -1. And the other one, which is 1, -3, is changed to 4, 9. Okay, so the currently unknown matrix A, B, C, D acting on the point 1, 2 gives me -1, -1. The currently unknown matrix A, B, C, D acting on 1, -3 gives me 4, 9. My 4 equations are A plus 2B equals -1, C plus 2D equals -1, A minus 3B equals 4, C minus 3D equals 9. At least now I can subtract right away. A minus A goes away. 2B minus -3B becomes 5B. -1 minus 4, -5. So B is -1. Once I know B is -1, that means A is equal to B is A minus 2 at A is equal to 1. C minus C goes away. 2D minus -3D is 5D. -1 minus 9, -10. So D is equal to -2. Once I know D is equal to -2, I get C is equal to 3. And therefore my transformation matrix is 1, -1. 3, -2. But again, that question, I actually like the old question better because it illustrates what happens when the determinant is 0. But I guess that's a little too advanced for this level. Question 11. A triangle with vertices. A triangle with vertices 1, 1. 3, 1, and 3, 3. Is rotated pi over 2, 90 degrees, clockwise about 0, 0. So if it's rotated clockwise, right, it's rotated into the 4th quadrant. So I should go there, and there, and there. So that's the rotation. Yeah, 90 degrees clockwise. I hope. I have such a hard time visualizing. I don't think that's right. So I'm not going to even bother. All I know is it's got a pi over 2 clockwise about 0, 0. Then reflected over y equals -x. let R represent the rotation and let T represent the reflection. A, write down the matrices for R and T. Well, I go to my clockwise rotation. Cosine 90 degrees is 0, sine 90 degrees is 1, negative sine is 1, cosine is 0. That's my rotation matrix. My reflection, y equals negative x, my angle is negative 45 degrees. Twice that is negative 90 degrees. Cosine of negative 90 degrees, sine of negative 90 degrees, sine of negative 90 degrees, negative cosine of negative 90 degrees. So there are my two matrices. B, find the single matrix that represents R followed by T. So R and then T after. Notice that R is on the right, T is on the left. 0, negative 1, negative 1, 0, followed by 0. Sorry, I wrote it as followed by, but what I meant is 0, 1, negative 1, 0, followed by 0, negative 1, 1, 0. R on the right, T on the left. So you get 1, 0, 0, negative 1. So C, hence, that means therefore, as a result of that, find the image of the triangle after both transformations. No problem. I will take my overall transformation matrix and have it applied to my 3 points, 1, 1, 3, 1, and 3, 3. So what do I get when I do this? I get 1, 0. No, not 1, 0. I get 1, negative 1. I get 3, negative 1. I get 3, negative 3. And D, from a sketch or otherwise, describe the single transformation followed by, represented by RT. That's got to be a mistake, because why would it ask for RT if the whole time it's done TR? But they don't say it's a mistake, but I think it's a mistake. Or maybe they want both. Maybe they want both. Let's do this one. So where do I end up on this one? I end up at 1, negative 1, 3, negative 1, and 3, negative 3. So this is my overall. So what we see is a clockwise rotation by 90 degrees followed by a reflection across the line y equals negative x is equivalent to a reflection over the x-axis. Now, for part D, it's asking for the single transformation represented by RT. This has got to be a mistake, but just in case it's not, 0, 1, negative 1, 0, 0, negative 1, negative 1, 0, or maybe they commute. Let's take a look. Do we get the same thing? So this one is negative 1. Well, already not the same thing. And then 0, and then 0, and then 1. So we get a completely different matrix, negative 1, 0, 0, 1. And when I look at my different forms that I have, this is a horizontal stretch parallel to the x-axis with scale factor negative 1, which means we are basically going to reflect it over the y-axis. It's a horizontal stretch of negative 1 scale, which means we're going to flip it. Just like TR was a flip over the x-axis, RT is a flip over the y-axis. And you can always check that by taking negative 1, 0, 0, 1 and applying it to your 3 original points and seeing what you get. I get negative 1, 1, negative 3, 1, negative 3, 3. So if I go back to my picture and I plot negative 1, 1, negative 3, 1, negative 3, 3, I do see, in fact, that in the other direction, it's a reflection across the y-axis. So now we go to question number 12. It says, let E be a matrix representing an enlargement scale factor 0.5. Enlargement scale factor 0.5 about the origin. A, write down the matrix, no problem. 0.5, 0, 0, 0.5. That's the easiest one. And then B, find a single matrix that represents a series of n enlargement scale factor 0.5 center 0, 0. So you do it n times. That's just e to the n. That's 0.5, 0, 0, 0.5 to the n. Well, how do you take a matrix to a power, to a whole number power? Well, in general, it's tough, but when it's a diagonal matrix, like this one here is, that's no problem. You just diagonalize each one individually, and that's our answer. Notice that each time it gets reduced by half. So 0.5 is a half, 0.5 squared is a fourth, 0.5 cubed is an eighth. It keeps getting smaller and smaller and smaller. Do it infinitely many times, and essentially you get nothing. And finally, our last question for exercise 9.4 is question 13. And this one is kind of cordoned off. There's like a line between 1 and through 12 and 13. So this one might be a little challenging. Let's take a look. You have the point P, which is -2, 5, undergoes 2 rotations R1. So R1 and then R1, followed by rotation R2. Right? So this is equivalent to R2, R1 squared. Because remember, we wrote right to left. R1, R1, R2, right to left. A, given that R1 is a counterclockwise rotation of 20 degrees. So R1 is that's clockwise. R1 is counterclockwise by 20 degrees. And R2 is a counterclockwise by 40 degrees. Then where do I end up with after doing R2 and then R1 twice, or R1 twice and then R2? Well, because I'm rotating in the same direction, I'm doing 20 and then 20 more and then 40. So overall, R2, R1 squared is basically an 80-degree counterclockwise rotation. So that means if I look at my counterclockwise rotation matrix, I get cosine 80 degrees, negative sine 80 degrees, sine 80 degrees, cosine 80 degrees. I apply that to my original point, -2, 5. And this one seems like it might be a calculator problem. 80 degrees is not a nice number in terms of trigonometry. So let's make sure we're in degree mode. And we do -2 times cosine 80 degrees minus 5 sine 80 degrees. So this takes me to approximately -5.27. -2 sine 80 plus 5 cosine 80, and I get -1.10. So that's where I end up approximately. B. Show that, okay, so this one is not challenging, but it is impossible if you don't know your trigonometric identities. It says, want to show that the following holds. Cosine 60 degrees, negative sine 60 degrees, sine 60 degrees, cosine 60 degrees, applied to the point xy, is the same thing as cosine 20 degrees, cosine 40 degrees, minus sine 20 degrees, sine 40 degrees. Underneath it is sine 40 degrees, cosine 20 degrees, plus cosine 40 degrees, sine 20 degrees. And the other ones is negative cosine 40 degrees, sine 20 degrees, minus sine of 40 degrees. Ooh, small. Cosine 20 degrees. negative sine 40 degrees, sine 20 degrees, plus cosine 40 degrees, cosine 20 degrees, xy. Show that these are equal. Well, you have to just know your trig identities. There's only two that you need. Sine of alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine beta. And cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. Let's take a look if these are on your formula sheets anywhere. You might not need to know these. I don't remember offhand whether or not you need any of your trigonometric identities, like a double angle formula, but this was possibly cordoned off. Yeah, it looks like you don't need to know this one, at least not by heart. But these are two formulas in trigonometry that connect sums of angles. And if you look at, for example, cosine of 60 degrees, well, cosine of 60 degrees is really cosine of 20 degrees plus 40 degrees, right? Make alpha 20 and beta 40 or vice versa. And you should get cosine 20, cosine 40 minus sine 20, sine 40, which you do. And similarly for the other ones. And just quickly, so this is you know, if you have these formulas, it's easy. If you don't have them, it's impossible. And then C, given that R1 is a counterclockwise rotation of angle alpha, and R2 is a counterclockwise rotation of angle theta, show that cosine of alpha plus theta, let's say you do them both. Well, if you do them both, if you look at that same formula we just used, it becomes cosine of alpha cosine of theta minus sine of alpha sine of theta, just by using that exact same formula. And sine of alpha plus theta is sine of alpha cosine of theta plus cosine of alpha sine of theta. So I think the reason why they were cordoned off is because they are formulas that are more advanced than you need to worry about. So that takes us to the end of exercise 9E. And now we go to the next portion, which is on affine transformations. But I think that this video is going on long enough, and I'm going to divide 9.4 into two parts. So this is 9.4a. And 9.4b, the next video, will be on the second half. So I will see you there.